In this video, I'll talk through the 2022 Advanced Higher Chemistry paper. I'll explain how I would approach each question. Starting off with our multiple choice, question number 1. With emission spectroscopy, we have electrons being promoted, and then as they fall down, they emit light. Each element does have its own specific characteristic spectrum. That's how you can tell which chemicals we've got. It's not visible light, it would be heat or electricity is used to promote them. Let's make that as our correct ones. The lines are to do with transitions between different energy levels, and they're also, if you've got a higher concentration of the chemical, you would have a higher intensity of radiation emitted. So those ones are all true, but we want the one that's not correct. Next one, how many electrons are in the highest energy subshell of chromium plus? First thing we should do is find out how many electrons chromium has. Chromium has 24 electrons. Following the Aufbau principle of filling the orbitals, we would therefore have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. We need to remember that chromium is one of our exceptions. And this is because instead of having 4s2, 3d4, which would be a full s orbital and a nothing of the 3d, we would instead have 4s1, which would be half filled shell, and we'd have 3d5. We lose the 4s before the 3d. So when it becomes a 1 plus ion, we have lost our 4s electron, which leaves 5 electrons in the 3d. That would make our correct answer D for number 2. In this one, we're asked about an octahedral complex. This would mean that there would be 6 bonds to the central metal ion. Bidentate ligands make 2 bonds. So we need 3 of the ligand. We've only got 2 in A and B, so I'm going to rule them out. If you've got 3 times L negative, that's going to give you a 3 negative charge. If you have 1 metal with a 2 positive charge, that means that overall you're going to have a 1 negative charge. Because of the ligands, there's more negative charges. Therefore, our correct answer would be D for this question. Heterogeneous, hetero means different. And our heterogeneous catalysts are in different states. They are found in the same state. That's not true, which means it is our answer for this one. They do adsorb the reactive molecules onto the active site, so on the surface of it. They provide different pathways with lower activation energy. Catalysts lower the activation energy. They do have unpaired d electrons. That's what allows them to make temporary bonds with the reactants, and then it progresses into the product. Correct answer here would be A. In this question, we have a disproportionation reaction. It's a redox reaction in which an element in a single substance is both reduced and oxidized. Okay, let's have a little look at what's happening here. Well, in this one, we have chlorine. So we have Cl2 going to Cl minus. Our potassium will be still positive in both of them because it's joined up to something else. And our iodine is going from 2I negative to I2. We have a redox equation, but it's not an element in a single substance that's doing both reduction and oxidation. So I'm going to rule that one out for that reason. Here, we've got iodines. Again, it's not a single substance undergoing this reaction. Again, I'm going to rule that one out. Next up, we have iodine. Going over to here. Only got it in one place, so I'm not buying that as my answer. Chlorine as well, it's only in one chemical. It's not both being oxidized and reduced. I'm looking for something that appears once on the left but twice on the right. So here we have chlorine. And we have our Cl2. When it's in sodium chloride, that's going to be Cl negative, so it's gained electrons and been reduced. when we've got it in NaClO, sodium is positive, oxygen is 2 negative. This would mean that this chlorine would then have to be positively charged. So in that substance, it has therefore lost an electron. So our chlorine at the start has turned into both positive and negative ion versions. That means that D would have to be our correct answer. In this question, the pH 7 is at room temperature. It will not be that at 325 Kelvin, so I'm going to rule that one out as well. The ionic product as well would be different at different temperatures. Again, I'm going to rule that one out. Our neutral solution will have to have the same number of hydronium ions and hydroxide ions. That makes that true. And again, with D at room temperature, we would have 1 times 10 to the power of -7 for our hydronium ion concentration, but it doesn't have to be that at different temperatures, because that will make it ever so slightly different. Next one, we are asked about equilibrium. An equilibrium constant. The pressure is increased at constant temperature. An increase in pressure favours the smaller side, smaller number of moles of gas. We have 3 to 2. So the concentration of the SO3 would therefore increase. Makes it A or B. In terms of the equilibrium constant, the equilibrium constant is only affected by temperature. Question is not changing temperature. That means A is our correct answer. We're looking for 1 mole of a substance being formed from elements in their standard states. Sodium chloride would be a solid, not a gas. I'm going to rule out that one there. We've then got ions for our sodium and our chlorine. That's not their standard state. In C, we've got Cl. Chlorine would come as a diatomic molecule, so it would be Cl2. We only need half of it because we do just want 1 chlorine. That makes D our correct answer for question number 8. Moving on to question number 9. We have got our rate equation given to us. The power of the 2 means that this is second order with respect to A, and we have first order with respect to B. Second order means double concentration, you quadruple the rate. And first order means if you double the concentration, you double the rate. So statement A, double A doubles reaction rate is wrong. That's describing a first order one. B is first order with respect to B, so that is going to be our correct answer. They have an order, which means they will have an effect. The ones that say no effect has to be wrong. Moving on to 10. Your orders must be found experimentally. This is where you'd repeat the experiment, changing only 1 variable at a time, identify what effect that has on the rate. It does not depend on stoichiometry. It is not the sequence of steps. It does not control the speed. It can only be found by experiment. Gives you that answer there. Here we're asked about disorder or entropy. If you have a substance in the solid state, the particles will be fairly closely packed together. This will mean it will be low entropy. As you start to warm it up, you will increase the entropy as they start becoming a liquid and they become a little bit more spread out. When we keep on going, we then get into gas state, where the electrons are more spread apart and you have higher entropy. At the point of changing state, entropy does not change when we're changing state. This means that we're going to have flat sections within our graph, meaning A and B are both incorrect. Of the 3 states, the gas is a lot more disordered than the solids and liquids. We want a big jump going from liquid to gas. we're starting off here as our solid, turning into a liquid as we increase temperature, and then we get to gas here. Biggest jump is between liquid and gas for C, and that one's going to be my correct answer. Moving on, we have ethine. That has got triple bond between carbons. If it was sp3 hybridization, that's what we find in alkanes. sp2 we find in the double bonds of the alkenes, and we are dealing with sp for our alkynes. Here we've got one s orbital and a p orbital mixing together, and that will leave two unhybridized p orbitals. In the top one here we have sp3 hybridization. We have one of the s orbitals and three of the p orbitals. sp3, not our answer. We have one s, we've got three p's. So used to them. So we're in this one, we're using up one of the s orbitals and two of the p's. sp2 again is not what we're looking for in this question. We then have the one s orbital and one of the p's coming together. That's then going to give us our sp hybridization. Last one, all that's happening, the p's are being left untouched, and the s shell has just increased in energy. That's not going to be our answer, and that gives us C for that question. We're asked here about sigma bonds. Sigma bonds are the first bond an atom makes. Have a little sketch these out. We have C double bond O. We then have two hydrogens and two hydrogens. This would have a pi bond. It's not going to be our answer. H2O is single bonds in the hydrogens and the oxygens. That will be our correct answer. Oxygen is diatomic and has a double bond between them, and nitrogen is also diatomic but has a triple bond. Not going to be our answer, so B for 13. Next we have bromine reacting with hydrogen halide. We need to look for our different steps that we're going to have. Here we need to look at the arrow between the carbon double bond and the hydrogen. It will be the electron rich double bond that will join to the H positive. This means I can then rule out the ones where the arrow is going the other way. Next, when we're dealing with these, it's either going to be a carbocation or it's going to be the cyclic intermediate. If we have a hydrogen halide, we would end up with a carbocation intermediate shown by the positive charge on the carbon, making A our correct answer. If you were using a halogen like bromine, so Br2, then that would have to react in a different way compared to the HBr. Next up, number 15, we're talking about a phenyl group. Phenyl group is when we have our benzene ring attached to one thing. In this one, we have a nitrogen in the ring, that's ruled out. B, we have a cycloalkane, not a phenyl group. Here, these phenyl groups are bonded twice. That's going to rule that out as our answer. And we do have a C6H5 joined onto that oxygen. We do have a phenyl group in D, making that our correct answer. Okay, next up, we have got an haloalkane. We are reacting it with a nitrile in a substitution reaction. And then nitriles undergo hydrolysis to form a carboxylic acid. Doesn't help us because they're all carboxylic acids. Let's sketch this out. We have 4 carbons with a chlorine. That is going to be replaced by a C triple bond N. And then when it undergoes its hydrolysis, that's going to then become a C double bond O, O, H. 5 carbons in the chain. That makes it pent. It's a carboxylic acid, so pentanoic acid is our correct answer. Nope. Here we've got 4 carbons with a chlorine coming off of the second carbon. We're then going to undergo a substitution reaction. And that's going to put on our C triple bond N. That's then going to be replaced and turned into a C double bond O O H. Our longest chain of carbons, including the C double bond O O H, is going to be 4. That would make it butanoic acid. We've also got a methyl group coming off of the second, so 2-methyl butanoic acid, making C our correct answer. Next one here, we should be able to recognise this is an ether. We're looking for the part with the oxygen. We have 2 carbons on the side with the O. That's going to then be ethoxy. When we look at our longest chain on the other part, we have 1, 2, 3, 4 carbons. And the ethoxy group is joining on the first carbon. That's going to make it 1 ethoxy. We have butane because there's 4 carbons. We also have a methyl group off of. This is the first one on this part. That's second. That's the third. So that's going to be 3-methyl butane. Might have been easier to actually do it the back to front way. So if we do it the other way, we deal with the longest chain, which is the 4. We have an ethoxy off of the first, which is 1 ethoxy. We have a methyl off the third, 3-methyl. And that gives us the correct answer of down B for number 17. In this question, we are told about ketones and chemicals called enols. They are tautomers. That means they can flip between them by rearranging their atoms. The double bond has shifted to be between 2 carbons, and instead of double bond O, we now have an OH. We can try that out with these ones. Okay, so to make that work, we want to make this now an OH group. We'd want to have a double bond between these carbons, and that would make this then CH2. That is possible, so not going to be our answer. Trying the next one, we can turn this into a single bond with an OH, make this a double bond, and that means there's only 1 hydrogen on there. Again, that does work, so not our answer. Next one, we want to get rid of the C double bond O. This time round, we'd need to put the double bond on the left hand side. If I put it over here, there's no hydrogen to be lost on the right, but there is one over here. Then this would now just be a C instead of CH, so that one will work. If we look at D, there are no hydrogens attached to the carbons either side of the carbonyl group, the C double bond O. So when I want to move a hydrogen over to there, I cannot put it on either side because there's no hydrogens here or here. That one does not have one of the enol tautomers. That means that it's not, sorry, that is going to be our answer because it's yet another. Which one does not? Which is rather unhelpful. Next one, we're looking for something that has non-superimposable mirror images. This means it has to have a chiral center. And this is a carbon that's attached to 4 different groups. When I'm working through these ones, I'm looking for the carbons. Here we have a double bond to an oxygen. That means that cannot be our chiral center. That means it could possibly be our central carbon. Here. We have a hydrogen coming off the top. We have then got an NH2. We have another hydrogen. And we have a carboxyl group on here. There are 2 hydrogens coming off of that central carbon. That cannot be our chiral center. Ruling that one out. Next up. Again, this carbon's got a double bond O, so it's not going to be our chiral center, but it could be one of our groups. CH3 at the top, it has 3 hydrogens on it. Again, won't be our answer. So we have CH3 group. We have a C double bond OOH. We have an NH2. And we also have a H. All of them are different. That means that central carbon here is going to be a chiral center, which means it will have non-superimposable mirror images. This one, we have a CH3 here and a CH3 there, so two of them are the same, ruled out. To the right here, there's two H's attached, so it's not that. And here we have three hydrogens attached, not that. Three hydrogens on these two, not it. Two hydrogens on these ones, not it. If we were to do our groups, we end up with a CH2, CH3 on the right. And that's exactly the same on the left. So both sides are the same. That means it's not going to be a chiral center. We do have an OH, which is different, and we have a CH3, which is different, but it needs to be all four things different. And that's why B is my correct answer. Number 20. We've undergone elemental microanalysis, and we want to work out the formula of the chemical. This means we are looking for an empirical formula. For that, we want to take the 0.12 grams of carbon, divide it by 12, which will give you 0.01. Hydrogen, we have 0.02. Divide that by 1 for hydrogen, it gives you 0.02. This means we're going to have a carbon to hydrogen ratio of 1 to 2. Counting these up, we have C4H4. That's not a 1 to 2 ratio. We have C4H6. Again, not a 1 to 2 ratio. We have C4H8. That will be our answer. We have C4H10, which is not a 1 to 2 ratio. So C is our correct answer for that one. Moving on. Here we have a molecular ion peak. That means if we look at the GFM of each of these, they have to equal 74. I'm going to, I think they're probably all going to be 74, but let's just double check. We're going to have 3 times 12 for the carbons, plus 2 times 16 for the oxygens, plus there are 6 hydrogens. Does equal 74. We've got 1, 2, 3 carbons. We've got the exact same again for the next one. That would be 74 as well. We've got 1, 2, 3, 4 carbons. That'll be 4 times 12 plus 1 oxygen this time, plus 8 hydrogens. That's 48 plus 16 plus 8. That's going to rule that out as our answer. And then the next one, we've got 4 carbons, so 4 times 12 plus 1 oxygen plus 5, 6, 7, 8 hydrogens. That's again going to be 72. That can rule that out as our answer. We now need to think about what peaks we would see if we start to break this apart. We would look something. From its formula, it looks like B is an ester. That would have CH3, then we'd have C double bond O and O, then a CH3. 15 could be from one of the methyl groups. If you took this part here, you would get 24 from the carbons, plus 16 plus 3. That gives you 43. That would tick the box for the 43 one. And then the 31 would be here. You would have oxygen 16, carbon 12 and 3 from the hydrogens. So that would be 15. And that gives you the 31. So our ester B would be our correct answer. Fits best out of all of them we've got. Okay, in this one we are given a mass of malic acid. I'm going to turn that into number of moles. We're doing mass divided by GFM. It gives us 0.05. Key to this one is it's an acid, which means we're looking at our carboxylic acid parts. We have 2 carboxyl groups. Next up, we need to look at a ratio between the malic acid and the sodium carbonate. If you were to use something like hydrochloric acid, which contains 1 hydrogen ion, you would need 2 of them to react with the sodium carbonate. Because our acid contains 2 carboxyl groups, that means we're going to have a 1-to-1 ratio, because one of the sodiums would replace the hydrogen here and the other one would replace there. Because it's a 1-to-1 ratio, that would mean that our correct answer in this case would have to be A for that. So it's diprotic, it means it can give 2 hydrogen, and therefore we only need one of them for the sodium carbonate. Next up, we are carrying out a gravimetric analysis. We have our starting sample, and we need to work out what would be the mass of calcium carbonate sample after heating to constant mass. Okay. So a couple ways of doing this. I would probably, first of all, let's get the GFM of this. We have 40.1 from the calcium, 235.5s for the chlorines, that's 71, plus 4 from the hydrogens and 32 from the oxygens. Gives a GFM of 147.1. There, the number of moles of this will be 2.52 divided by 147.1. That gives me 0.01713 moles, we'll call it. We are then going to be losing out the water, but we'll still have the same number of moles of calcium chloride. So if I redo my GFM, but this time I'm going to ignore my hydrogens and our oxygens, that would give me a GFM of calcium chloride without the water as 111.1. If I do the mass of that by doing N times GFM, that gives me an answer of 1.9, which would give us an answer of B for this one. The alternative route we could take is we could work out what percentage of the compound is calcium chloride. To do that, well, we take it to GFMs, and then we've got 111.1 divided by the total GFM, including the water, would be 147.1. Times that by 100. That means that 75.53% of the sample is the calcium chloride. If we then work out 75.53% of the 2.52 hydrated sample, that will hopefully give us the same number, 1.9. And again, it does give you that exact same value. So either way works, whichever one works best for you, we still get to our correct answer of B. In this question, we're asked to purify and identify a compound. In a distillation, we separate substances based on their boiling points. That would allow us to identify the chemical based on what that boiling point is. That looks like a good answer. Recrystallization purifies but doesn't identify. Solvent extraction would be used to remove impurities and purify. Melting point apparatus would allow you to identify based off its melting point. You can compare it to literature results of it, and that would be our correct answer of A. In this question, we're asked to analyse a chromatogram. We're asked which conclusion must be correct for this. Okay, so we've got our pure sample. For C, we've got the pure reactant and the reaction mixture, whereas S is just the reaction mixture. Which of the following must be correct for that one? The reaction mixture does not contain any impurities. If there were impurities that had the same retention factor, they would be found underneath the spots, so we couldn't actually see if there were impurities. So that one can't be there. All the reactant is used up, but at the end there is no reactants left over because the spot for R does not appear in our sample S. So that one looks like it would be the correct answer. We don't know if it's only the desired product. We know that there's only one spot here, but again, if they had the same or similar retention factors, they could be doubled up and you wouldn't see the different ones. This gives no indication of how far along the reaction's gone. It might have only made a little bit of this chemical. We don't know. We just know that there's no more of the original chemical R left because it doesn't appear in our chromatogram. And that brings us to the end of that paper. Moving into paper 2, we're asked to draw the shape of a p orbital. If the question was wanting an s orbital, that is just a circle. We have a dumbbell shape for a p1. It can be an area on orientation because we're not told which specific p orbital we've got, so any of those ones would work. Here we're asked about a 2p electron in oxygen, so the principal quantum number has to be 2 because it's in the second shell. If it was an s orbital, then our L would equal 0. If it is a p, then our L will equal 1, which is what we've got now. In a p shell, we've got 3 possibilities. And that means for our ML, it ranges from minus L to positive L. What that means is we could have either 1, 0, or minus 1. And we get to pick which one we're going to do. I'm just going to go for 0 right in the middle. And then our spin number is to do with, is it the electron pointing up the way or the electron pointing down the way? Again, it doesn't matter which one we pick. We could pick positive a half or negative a half. I'll just go for the positive one. And that would be our quantum number for there. We could have picked the 1 or the minus 1 or plus a half or minus a half for the bottom value. It doesn't matter because they're given us the options in this question. In this one, we're asked about ionization energies. So that's the energy required to remove electrons. Talking about oxygen and talking about nitrogen. First, sketch out some box diagrams for oxygen and nitrogen. Oxygen's arrangement would be 1s2, 2s2, 2p4. Our nitrogen has 1 less electron. The half filling of an subshell will provide extra stability. This question is asking you about the oxygen, so I'm going to start talking about that first. Oxygen does not have a half filled p shell or subshell, and that means it's a less stable arrangement. And that makes it easier to remove that electron. And that would explain that one. Next up, here we're talking about an energy associated with a particular spectral line. We're given an equation. We're going to have to try and pop these into this. So we want the energy, which is good. We don't have to do any rearranging. So E equals, it's going to be 2.18 times 10 to the power of minus 18 times Z, which is the atomic number. Atomic number of oxygen is 8. You'll find that in here if you are unsure. So we have got to multiply that by 8 squared. Open some brackets. We have 1 minus 1 over principal quantum number of the second energy level. Well, second energy level's principal number will be 2. So it will be 2 squared. We can start to work it out, or we could just make the calculator do all the work. I'll write it out a wee bit more, where we've got 64, and that's going to then be 1 minus 1 over 4. And then let's just lean on the calculator. And that gives us a rounded answer of 1.05 times 10 to the minus 16. And that would be in joules, as it says there. Question 2 gives us the enthalpy change and also tells us about the entropy. This question, and to do with feasibility, we want to use our relationship delta G equals delta H minus T delta S. If the reaction is feasible, we will have a negative Gibbs free energy, so negative delta G. Start to put in our numbers that we've got. To get your overall change in enthalpy, the delta H, we are using our products, take away our reactants. Both the reactants, they say, is 0, so we can ignore them. That means our delta H is going to be 90.3. When we're doing questions like this, we need to make sure we are either both using kilojoules or both using joules. I find it easier to turn them both into joules. 90.3 kilojoules will be 90,300 joules. Just timesing it by 1,000. We've then got minus T for temperature, 298. Over here, we need to do, again, the products take away the reactants. That will be 211, take away half of 182 and half of 205. And that gives a value of 12.5. Pop that in over in our other equation. That gives 86,575 joules per mole. Or if you wanted to keep it in kilojoules, you should have ended up with 86.575, or that rounded up. That would be the kilojoules per mole. Either way, that is a positive delta G. Therefore, it is not feasible at this temperature. In this question, we're dealing with parts per million. It can either be described as milligrams per kilogram, or, which will be more helpful in this case, milligrams per litre. Question says we've got 2 parts per million, so that would be 2 milligrams in 1 litre. We have 5 litres, so we're going to times this by 5, scale it up, so that's 10 milligrams in 60 litres. It says that that's per minute. We're asked about an hour, which is 60 minutes. Therefore, we would have 60 times as much, which would give you 600 milligrams. You could change it into grams, the point, but you could, and that would be, if you did that, it would be 0.6 grams. For this question, we need to be aware the oxygen is in group 6. It would gain 2 electrons and have an oxidation number of -2. That means in this first one, we have to have a +2 charge on the nitrogen, because then they balance out and we have a neutral overall compound. Next, we've got oxygen again, but this time we've got 2 of them. So it's going to be 2 times -2. If we've got -4 on that side, the nitrogen in this case has to be +4. Put that in there. Here we've got 3 times our -2, overall -6. That is split across 2 nitrogens. That means each nitrogen has to be 3 positive. And then we've got 2 of them, which balances it out. So that has to be +3 as our answer. Next up, we want a rate equation. This has to be on the slow step. That means we only care about the top one. The way that this works is that rate equals the rate constant, which is lowercase k. And then we want the concentrations of the reactants involved in step 1. We have our nitrogen monoxide. Because it has a balancing number of 2, we want to put the power of 2 for that one. Whereas our hydrogen is just going to be by itself, where we get this. So now the question wants us to use that information we've got to calculate the concentration of the nitrogen in this particular experiment. We are told that the rate is 0.004. K to tell us as well. 3. Then we don't know our concentration of nitrogen monoxide, but we do know that that is times 0.015. Rearranging this, we are going to want to know what our nitrogen monoxide is. If we then rearrange it, we're going to have our rate being divided by 2.7 times 10 to the power of 3 times 0.015. Once we get that value, we need to take the square root of that to get us our final answer. Taking the square root of that gives us 0.00994, and that's in moles per litre. Next, we're asked for a balanced equation for the overall reaction. We're looking to see if there's anything that appears on each side that can cancel out, or things that can be combined together. We have N2O gas on both sides, they can cancel out. These two hydrogens will combine together because they're on the same side. Same with our waters, that gives us 2NO gas plus 2H2 gas goes to N2 gas plus 2H2O gas as well. We have got 2 nitrogens on the left, also 2 on the right, that's fine. We have 2 oxygens here, 2 oxygens there, also fine. 4 hydrogens, 4 hydrogens, that would be your balanced equation. In this one, we're asked about a weak acid. This is about dissociation. Weak acids partially dissociate into ions, whereas a strong acid would fully dissociate into the ions. We have an acid, add it into water, and it splits apart partially. Next one, we have been told we've got a weak acid, it says at the top. We want to calculate the pH of this solution. For weak acids, we want to use pH equals half pKa minus half log to the base 10 of C. That's pH we want, equal half of. In the data booklet, it should have our pKa that we need. Down to page number 4, that gives us a value of 3.2. That's minus half of log to the base 10 of 3.75. pH therefore equals, that'll be 1.6, 0.287, and that gives us a final answer of 1.31 as our pH. Next question asks us about the percentage by mass of the solution. Anytime I've dealt with percentage by mass, I'd be using the mass divided by the GFM times 100. That's not going to work in this situation. In this situation, we are dealing with solutions, so we are looking for the mass per 100 centimeters cubed. And what we are told is that there are 3.75 moles in 1 litre. Therefore, in 100 centimeters cubed, or 0.1 litres, that should leave us with 0.375 moles. Hydrogen fluoride, HF. Hydrogen has a mass of 1, fluorine has a mass of 19 there. That gives you a total of 20. Then we want to do 0.375 times 20, and that would give us 7.5%. That would probably have thrown me off quite significantly. Like I said, the one that I'm more used to, but in this one, this is how we would approach that question to get our answer. Next one, we're talking about the shape. We are going to use VSEPR theory, valence shell electron pair repulsion. We need to look at the central element, which in this case is silicon. We need to look for how many outer electrons it's got. Silicon is in group 4, so that means it's got 4 valence electrons. We are then joining 4 things to it. Each of the fluorines would count as 1. That gives us another 4. That means that we've got 8 electrons. That will give you 4 electron pairs. All of them are involved in bonding. This means that it will be based on and have the shape of tetrahedral. So the shape of the electron pairs around the central silicon would be tetrahedral, as would the actual shape of the molecule, because there are 4 fluorines going around it. Next up, we have got a condenser used in the vertical position. This prevents any volatile chemicals from escaping. That is how we carry out our reflux. Whenever we are using our round bottom flask, or if we're carrying out a reflux, we want to add anti-bumping granules just to make sure things don't get out of hand. Okay, in this one, we're dealing with the salt of a weak acid. If we're adding more hydrogen ions, the equilibrium would shift to the left. The conjugate base, which is the negative part of the salt, would pick up on the hydrogens and we'd form our undissociated acid. Getting that across, conjugate base reacts with hydrogen ions, form the undissociated weak acid molecules, like it says in the question. Next, we've done some recrystallization. We want to have quick filtration. That's done under a vacuum. We use a vacuum pump to pull out the air, and that will just make sure everything falls through a lot quicker. Recrystallization is an attempt to purify substance. That's the hippuric acid. Could mention the fact that we are removing the impurities. That makes it more pure. This one, we've got an infrared spectrum. Infrared spectrum to do with vibrations. There are characteristic vibrations for different bonds. The reason why they absorb different wavelengths. Have different and bonds. Another approach would be that they are different strengths. State wave number of the peak in this spectrum caused by an NH bond. We can go through data booklet first of all. We're looking for the peak between 3,500 and 3,300. That's going to be the peak at the far left. We run this down. Right in the middle, that would be 3,500. This would then be 3,400. So we're looking for something around about there. I'm going to just go for 3,350. That's in. Here we're looking for the environments. So our first environment would be the hydrogen from the carboxyl group. Both of the hydrogens attached to the carbon here. That would be your second environment. We then have a hydrogen on the nitrogen. That would be a different one. When it comes to the benzene ring, when it comes to our next carbons, both of these two are next to carbons with one hydrogen on them as part of the benzene ring, and they're also connected to this carbon here, which is going to be affected by the carbonyl group. So both of those two would be the same. The next two would be a different environment. That would be that one and that one. And then we'd end up with our sixth environment would be that hydrogen that is on the end, like, of the molecule. That's 1, 2, 3, 4, 5, 6 different environments. The benzene ring ones are always quite tricky to get. If you just had a benzene ring, this would just be one environment. They're all the same. It makes a difference that it's connected to different chemicals. That does change up how many environments that we have. When we're dealing with splitting patterns, we need to look at how many hydrogens are adjacent to this hydrogen here. We have one hydrogen to the left of it. The n+1 rule comes into effect here. So if there's one hydrogen next to it, that means that we will see two peaks, which would be doublet. How does NMR work? First thing is that the hydrogen nuclei align with the magnetic field. Different wavelengths are emitted for different environments. What is surrounded by will have an impact on the energy gaps, and that will change what wavelengths we are able to see. In this question, we're asked to comment on the pH of urine and dealing with 3 drawn out chemicals and also some other chemicals named above. Talk about weak bases and acids. We could then give them some of the equations from the data booklet. It mentions carboxylic acid, so I'm going to deal with ethanoic acid. And then ammonia, we have NH3 with our water, associate into ammonium plus our hydroxyl group. We could talk about the pH of salts. If there's acids and bases, we could talk about neutralization. So if you have strong acid and strong base, you'll get a neutral salt. Strong acid, weak base would give you an acidic salt. And if you had it the other way around, weak acid and strong base, you have an alkaline salt or basic. We could go on to explain why this would be the case. So we have an acidic salt added to water. And if we had ammonium chloride, a little bit messy here, but that would be from ammonia, which is a weak base. And then hydrochloric acid would be my strong acid. So we'd make ammonium chloride, that would have NH4 positive and Cl minus. Our hydronium ions and our hydroxide ions. And it makes it easier to just talk about the H+. We might have some of the NH4 and OH negative would react to form a weak base. This leaves excess of our hydronium or hydrogen ions. That's what leaves you with the pH of being less than 7. Doing it the other way around, if you wanted to do it for our basic, so it'd be the other way around, where the H pluses would form a weak acid, and then that would then leave more OH minuses. We could talk about using the relationship to work out the pH of a weak acid or weak base. You'd use the dissociation constant for the base, not the one for the acid. Don't even look at that. Could perhaps put numbers in there just to explain what each of them are. We did do that in a previous question, so that's why I'm less tempted to go down that route, but it is a possibility. Could also talk about the ionic product of water. Talk about how that's at particular temperatures. Changing the temperature would affect the equilibrium. With all these questions, we need to get a good answer to get 3 marks, a reasonable answer to get 2 marks, and a limited answer would get you 1 mark. Quite possibly a lot more things we could have talked about, but as long as we get enough to pick up the good answer and get our 3 marks, then we are happy. Then I would be happy with that. Splitting is caused by repulsion of the lone pairs and ligand. And those lone pairs are the non-bonding electrons, and they would cause that splitting in the complex. Next up, we've got Aufbau principle. One of a few principles we need to be aware of. Orbitals fill in order of increasing energy. What that means is that we want to have electrons in the bottom before we go to the top. We don't start top down. We are given a table of information. We're trying to give 2 conclusions based on this. Our high spin has a lower difference in energy. And we're actually wanting 2 examples. Change this up. The cyanoligand Cn negative has caused greater difference in energy. I think those would be my 2 we're going for. Here we've got our complex ligand. We have got fluorine. And these questions for transition metals, we call that a fluorido. There are 6 of them, so it's going to be hexa fluorido. Because we've got a negative charge on the whole complex, that means instead of saying cobalt, we need to use the name cobaltate. If that was 3 positive, that would be cobalt. As it stands, cobaltate. Each fluorine has a 1 negative charge. We have 6 of them, so it's going to be 6 negative. If you've got 6 negatives in fluorine and overall we have 3 negative, our cobalt has to have a 3 positive charge. That means we're going to have hexa fluorido cobaltate 3. Show the arrangement of d electrons in that same ion we have done. So what this will mean is we have cobalt, but we've lost 3 electrons. Okay, cobalt, we have 27 electrons. So our cobalt in its ground state would look like that. To make it 3 positive, we're first going to lose our 2 4s electrons, and then instead of being 3d7, it's now 3d6. If we go up to the top here, it tells us it's in a high spin state, which means when we go up to here, it means that we are filling all the boxes with 1 electron first before we double up, whereas in the lower one, we'd fill up the bottom row first of all. We have 6 to deal with. We'd still go 1 in here, 1 here, 1 here, then have 1 here, 1 here, and then we would start to double up with our 6 electron, giving us our high spin arrangement for this particular complex. Next, we're looking for a chromophore. Chromophores have conjugated systems. And what that means is there's alternating single and double bonds. Here we want to make sure we are including our single and double alternating bonds. We would have that one there, and down the bottom, this section of atoms here, and either of them should count as your chromophore. That's part that causes the colour. Next up, we're talking about bonding and anti-bonding orbitals. In our little diagrams, the anti-bonding ones are higher energy. That's why they're less likely to contain electrons. Higher energy anti. In fact, it says state 1 difference makes me think there might be another one. I can't think of anything off the top of my head. But yeah, talking about different energies. So antibonding, higher energy, which makes it less likely to find electrons there. We've got cis and trans isomers. And why can they exist with carbon-to-carbon double bonds? Well, the first thing is that it stops rotation. Rings work as well. A ring of carbons would do the same thing. So that's the first half of it. The other thing we need to have different groups. For example, if you had 2 hydrogens attached to that one, and then you might have had CH3 and C2H5. Both of these groups, the non-hydrogens, are on the same carbon. You cannot rearrange that to have both of them on the same side or both of them on opposite sides of the double bond. If you had, however, something like this, let's say we had a chlorine here, these are both on the same side of the carbon-to-carbon double bond, so that would be our cis version of this chemical. And if you were to swap those two around, this now becomes your trans version of that chemical. Next up, we're looking to show an internal hydrogen bond. Here we're looking for a hydrogen attached to F, O, or N. So here we have a site for hydrogen bonding. That's then going to be attracted to another one where we've got this OH here. So we could do a dotted line. So from the nitrogen there, the hydrogen there. And then your other option would be a similar thing over here, from the oxygen to the hydrogen, or the hydrogen to the nitrogen on opposite functional groups. Here, yellow bilberine changes into compounds that can be extracted by otherwise blue light for that. If we check out our colour wheel, we can see that blue and yellow are complementary. They're across from each other in the colour wheel. So blue is complementary to yellow. And if the chemical is yellow, that means it must absorb its complementary colour. If it appears yellow, that means it absorbs the blue light. Here we've got a calculate energy question. This question, because we're wanting it in kilojoules per mole, we're going to use E equals LHC over lambda. E is what we're looking for. We can find these constants on page 20 of the data booklet. So for Avogadro's constant, 6.02 times 10 to the power of 23 times Planck's constant, which is 6.63 times 10 to the minus 34 times C, which is 3 times 10 to the power of 8. That's going to be all over. We want our wavelength in meters to use it in here, which would be 4.465 times 10 to the minus 9 meters. This will kick out a value in joules, which we can then divide by 1,000 to get to our kilojoules answer. I'm going to let the calculator do all the heavy lifting in this question. That gives us 257,501 joules per mole. They want us to give it in kilojoules per mole, so divide by 1,000 to get your answer of 257,258, which you can get 257.5 or 258 if you have it rounded. In this question, we're asked about the process of weighing by difference or measuring the mass by difference. A couple of options for this. First thing I would do is I would measure mass of container plus sample. Then you're going to transfer the sample out of your container you measured it in. You want to re-measure the mass of the container. If you do the mass of container plus sample, take away mass of the container, that will equal the mass that was transferred. Not all of the sample would transfer from your weighing boat or plastic boat, so this just allows you to see exactly what you did transfer and not use the wrong values in your calculations. Next up, we are reading off a graph. We're told the absorbance was 0.42. Now we've got one box up from the 0.4, run that across, run that down. Along the bottom, each box has to be 0.1 times 10 to the power of negative 4. So we have a value of 2.1 times 10 to the negative 4. And that's in moles per litre. Based on the question, it tells us that we've got 100 centimetres cubed of the sample. We can work out the number of moles of the manganese ions by doing N equals C times V. That's that 2.1 times 10 to the minus 4 times 0.1, which will just reduce the power. So it'll be 2.1 times 10 to the minus 5 moles. We can then work out the mass. Mass equals N times GFM, which equals 2.1 times 10 to negative 5 times GFM of manganese is 54.9. Gives us 0.0011529 grams. Here, what we've got is we've got the 0.0011529 grams over the mass of the fertilizer was 5.66. We need to use that value. So out of that 5.66, there was that small number, times that by 100. This is probably going to be a tiny number. Maybe even small enough to make people think they've not done it the right way around. Gives you 0.02%. That seems unnecessarily small. This question tells us about a chemical used to kill moss. Characteristic that makes it as suitable as a primary standard. It has to be readily dissolvable, readily soluble. Or we could talk about having a high GFM, so in our calculations the errors are quite small. We want it to be stable in water, stable as a solid or solution, or available high purity. That's the one. High purity. And if a question said, why is this not suitable, that means it has to not tick one of those boxes. And you can figure out which one that would be. Next up, we've got a bit of a calculation going on. Question wants us to talk about iron, 2 ions at the end. We're told the concentration and volume of the potassium dichromate, Cr2O7 to negative. We can use N equals C times V, and that would give you 0.005 times 0.0214. Loving the small numbers today. There's your little number here. Key with these questions is we are going to need to scale them up at some point, and that's how they make it a little bit different from what we did at higher. Our chemical was made up into a 250 centimetre cubed flask, and we used 25 centimetres cubed at a time. That means that there's going to be that number of moles in 25 centimetres cubed, which means we'll have 10 times as much. So drop one of the zeros. Moles in 250 centimetres cubed. You could scale it later. I just like to get it out of the way because I am liable to forget. So I would deal with that as soon as I can. We then want to do our ratio between the two chemicals. There is no number in front of the dichromate. That's a 1. There is a 6 in front of the other one. That is a 6. That means that we've got 0.00107. We need 6 times as much as that. 0.00642. That's now our number of moles. We are asked for the mass, and that equals N times GFM 55.8, and then that gives us our final answer of 0.358 grams. Again, in this question, we're talking about a conjugated system. We have to be thinking about our HOMO and LUMO, our highest occupied molecular orbital and our lowest unoccupied electrical orbital. This would mean we'd have an electron in our HOMO, and that's going to be then promoted to our LUMO. Okay, if we see violet, that means that we're looking for the one that's opposite in the colour wheel. So for us to see violet, that means yellow green light must be absorbed, and that's what's then going to promote them up to the lowest unoccupied molecular orbital. So yellow, green light is absorbed and electrons promoted from the highest occupied molecular orbital to lowest unoccupied molecular orbital, or HOMO to make life a lot easier for us. Next up, we have to write a formula for leftover chemical in this reaction. Okay, start to cancel these away. We've got 3 CH3s on both sides. We've got 3 COs on both sides. We have 3 chlorines here. We have 3 chlorines there. And that's going to leave us with a P. We've got 3 oxygens and 3 hydrogens. How would you write this then? So that would be... No, the order shouldn't matter, but it might look nicer. We do something like that. Okay. And that gives you the same numbers on each side. So that. Nucleophiles are attracted to positive charges. That means that it could be a negatively charged ion. The fact we've got a chlorine in it, so here we're looking for the nucleophilic attack step. We've got our polarity here due to the differences in electronegativity. We then have an attraction between the negatively charged oxygen towards the positively charged, slightly positively charged carbon. And that would give us our first step in here. To draw a structural formula for the ester that would be formed in this reaction. So based on the fact we've now got our attraction there, the hydrogen and the chlorine would come off, and now we need to make our ester link. So an ester link is C double bond O and then an O. We've then got to deal with our 2 carbons, which are on the left hand side, our acid side. Let's pop them in like so. Next up, we've got our oxygen. Now that is attached to this carbon here. I'm going to do this CH3 going down the way, just so it doesn't take up too much space. We've then got the hydrogen. We've got another carbon with the hydrogen. I'll make that a CH3. Then got our CH2 and a CH3 to finish with. And that would work out. To make that a little bit nicer, I'll just make them both the methyl branches, I'll just make them CH3s. Look a tad neater. Make sure all the bonds are going to the correct places. Make sure we've got enough bonds and enough H's. That should work out. Well, the other product, just set it at the top there, it's going to be hydrogen chloride or HCl. In the preparation of esters that you are probably more familiar with, you need to add a catalyst of concentrated sulfuric acid. If you think back to when you first made esters, your teacher would more than likely have put in the drops of sulfuric acid for you. This reaction is a lot quicker. That means no catalyst is needed. We're asked about the type of amine used. We're talking about primary, secondary, or tertiary. The nitrogen is attached to 2 carbons. That makes that a secondary amine. What group of compounds does Y belong to? This is the functional group here. C double bond O to an N. That is going to be an amide link. We've got there. When we are adding on to benzene rings, that's going to be electrophilic because they have the delocalized electrons. Let's just one out. And then we're swapping, so substitution. Next up, we have a percentage yield question. Percentage yield equals the actual over the theoretical times 100. We are told that we actually produced 18.4 of the benzophenol phenone. That's going to be my top number here. We are told how much of a reactant we've got. We need to work that through to work out how much of the product we could make. And that just involves a little 3-step calculation. So N equals M over KFM. 21.8 over 140.5. 0.155 moles. we look at the equation up here, it's a 1-to-1 ratio, they're just joining together. That means of our benzophenone also have the same number. And we want to work out the mass, which is N times GFM. So the 0.155 times 182 gives us 28.21. Pop that in as our theoretical. It needs to be times by 100 to give us our final answer. 65.2%. In our second using your knowledge of chemistry question, we're asked about elimination reactions and nucleophilic substitution reactions. We're discussing 2-bromopentane, so I'd first sketch that out. If we react it with sodium hydroxide in an ethanol solution, we will carry out elimination. So we need ethanol for elimination. An elimination reaction, what happens is we lose, in this case it'd be the bromine, we'd lose one of the hydrogens and one of the carbons beside it. And then we're going to form an alkene. This would be pent-1-ene. The other thing that could happen is we could lose the hydrogen from the right hand side. That in this case would give us a different product. That would give you pent-2-ene. The reaction conditions would be quite important. That is elimination. Next up we could talk about the nucleophilic substitution. We're using our sodium hydroxide. This would form an alcohol, which would be pentan to all. We could kick off from there into talking about SN1 and SN2 reactions. An SN1 reaction happens in 2 steps. SN2 happens in 1 step. The chemical we're dealing with is a secondary haloalkane. Primary haloalkanes are more likely to undergo SN1, more likely to undergo SN2 reaction. Tertiary haloalkanes more likely to undergo SN1 reactions. We have a secondary one. That means that it could happen in either way. No one that's more favoured than the other one. I'd probably leave it there for that part because talking about identifying them as well. A few options for this. Infrared spectroscopy would give an idea of which bonds we've got in our substance. We're dealing with alkenes and alcohols. That means if we look in our infrared table, we can look for the values that we'd expect to get if we have alcohols here. So we'd be expected to see values in these sort of ranges that we've got. So I'll go for the 3600 to 3200. Our alkene is likely to be down 1680 to 1620. Freeing up some more space, we could also talk about mass spec, which would separate out and show us different possible fragments of the molecule. If you have a fragment of 17, that could be an OH group. And you could look at how they're arranged as well and see possible options. NMR would give you an idea of how many hydrogen environments and how the hydrogens are arranged next to each other, which could give you more information about which chemical we are dealing with. Again, quite possibly lots more we could talk about. That's everything I can think of at the moment. 3 marks for a good answer, 2 for reasonable, 1 for limited, and hopefully I should pick up the majority, if not all of those marks. On to number 10, we're discussing drugs, and in this case, an antagonist. An antagonist blocks the receptor, and by blocking the receptor, it prevents the response. How I think of this is a protagonist in a story is the main character. An antagonist is doing everything they can to stop the protagonist from doing what they want to do. They're getting in the way, they're blocking the receptor in this case, and that prevents the response. If the question wanted the other type, which is an agonist, and they mimic, bind to the receptor, and they'll trigger the response and make that happen. In this one, we want to prepare 500 centimeters cubed of a stock by diluting it with water in 1 in 100. Therefore, if we're using 500 centimeters cubed, then we need 5 centimeters cubed. Then that's 1 out of the 100 for that. Is a bit straightforward. That would be the answer there then, would be 5 centimeters cubed. Okay, this question we're asked about density. In density, we have the mass divided by the volume. What are we trying to figure out here? We could say then density is 0.91. That would be 0.921 grams in 1 centimeter cubed. We want moles per litre. That's 1,000 centimeters cubed. We want to times this by 1,000 to give us 921 grams in 1 centimeter cubed. So then we turn that into number of moles by doing mass over GFM. That'll be 921 divided by 154, I should say. That gives us 5.98 moles per litre. But our stock solution was done by a factor of 100. So that means it's going to be 100 times less concentrated. That would give you 0.0598 moles per litre. If you had a 50-50 split, a 1 and 2 dilution, it would half it. Here we have a 1 in 100, so that's going to divide it by 100, and that should give you your correct answer for that question. Next up, we've got more dilutions. We've got a new concentration, and we want to know the number of molecules that we have, and we've got 1 litre. So if N equals C times V, our concentration is the value they've given us, the 9.97 times 10 to the minus 24. It's 1 litre, so it's just times 1. So that is our number of moles then. 9.97 times 10 minus 24. They're telling us that 1 mole would give us 6.02 times 10 to 23 molecules. And we want 9.97 times 10 to minus 24. Go from 1 to any number, you want to times by that number. So times by 9.97 times 10 minus 24. And I should just have to do the same on the other side. 24. And that gives us 6.00194, so 6 molecules. Again, seems like a really rounded number. That looks about right. Yeah, scaling it down. We've got quite a low concentration, so it would make sense that the number of moles is quite low as well. So we'll say here, write the molecular formula for caffeine. And what we need to check for are there any hidden hydrogens? So the end of each line is a carbon. So that means there's 3 hydrogens there. Nitrogen is making 3 bonds, that's fine. We would need 1 hydrogen here. No hydrogens on that nitrogen. This carbon is making 1, 2, 3, 4, so that's fine. We have 3 hydrogens coming off of this one. No hydrogens there. None there, but 3 more here. Just checking I actually looked at the right chemical. We have got, for our carbons, we've got 1, 2, 3, 4, 5, 6, 7, 8. Hydrogens, we've got N in total. Nitrogens, there's 1, 2, 3, 4. Then O2 to wrap it up. With this question, it shouldn't matter which way around you put them, but that's the way I would do them anyway. Why can these, so we're asked why both of these chemicals can bind to the same receptors. There must be some common fragment, there must be a group of atoms that is the same in both of them. Just having a little hunt for it. I think I've spotted parts of it. So bits I'm looking at is we have our ring of carbons and nitrogens as we do over here. It's a little bit different when we go over. There are nitrogens down here, but they're double bonded, but there are enough overlap that they would be able to work together. It's another one of those questions, because it's saying they can bind to them, it must be that they've got a similar shape. That's why things can bind to the same receptors. In this question, we are doing a solvent extraction using dichloromethane. This one, you want to use a separating funnel. Add the mixture to a separating funnel. We're going to shake the mix. We're going to allow to settle. That takes quite a long time in some cases. And then you want to run off your lower layer. And that would have your 2 different, and that would give you your 2 separated solvents, and then you'd be able to see how much caffeine is in each of them. And I think they have told us this. So we're asked to work out an equilibrium constant for both of them. Right, so we need to think of water. We need to think of dichloromethane. Now, get our equilibrium constant. We're going to want to do whatever the concentration is in dichloromethane. That would be divided by the concentration of the caffeine in water. Okay, we're told the mass in the dichloromethane is 23.5. We have our total mass is going to be 32. That means if we take them away from each other, that gives you how much would be found in the water. So that should be 8.5. Because we have different volumes involved, we have to take them into account. And the volume of water is 100, that's a soft drink, and then 60 for the dichloromethane. The concentration, therefore, will be the mass divided by the volume. 8.5 over 100 and 23.5 over 60. I'm not using the moles over GFM because they're both caffeine. If we found out a GFM of that and then divided them both by GFM, they're still going to be in the same proportions. So I'm just going to use the concentration as being grams per centimetre cubed in this case. That will give you 0.085. And then for dichloromethane, it'll be 0.392. And then hopefully, if I just pop these numbers in the correct order, 0.085 and K would equal 4.61. And this would make sense because if you look at how much we've got in our dichloromethane, it's much more than is left in the water. So our K would be a positive number, and 4.61 looks right to me. An improvement to do this, instead of doing it all as one extraction, we want to carry out the extraction with multiple smaller volumes, and then that will give you an overall greater quantity of caffeine extracted. What I mean by that is, instead of using all 60 together, instead of doing one extraction with 60 centimeters cubed of dichloromethane, you could do 3 times 20 centimeters cubed, and then you combine all the layers, and that would give you a greater quantity that's been extracted. Final question we've got here. We're talking about Svitter irons. This is something I vaguely remember from first or second year at university. They're telling us that this means it's a molecule with positive and negative charges on different atoms, and overall it's electrically neutral. We're showing here the movement of the electrons to form this positive and negative charge. We're asked to complete it to show all the charges on this molecule. If we look at what happens with this nitrogen down here, we are becoming positively charged, which would suggest that this would also become positive charged. And then the oxygen, like this oxygen, is becoming negatively charged. And that would give you your positives and negatives. But again, there's 2 positives and there's 2 negatives in the bottom one, which means it would overall still be neutral for that. I don't see any other way of doing it. It fits the bill, positives and negatives, and also neutral. So that should hopefully work out for that one. That brings us to the end of the paper. That's how I would approach each of the questions. Thank you for watching. Goodbye.